All right, today we're going to do something a little different. We're going on a journey to map out the very things that make math work, numbers themselves.
I mean, think about it. We use numbers all day, every day, right? They're on price tags, on the clock, on your phone. But have you ever really stopped to think about where they all fit? Like, if you had to draw a map of all the numbers, what would that even look like?
Okay, let's try a little thought experiment. Picture yourself standing on a road, an infinitely long road, and you're right at the spot marked 0. This is the number line. Now you've got this big empty bag, and your goal is to walk down this road and collect every single type of number you come across.
So where do we start? Well, first things first. We gotta bag the basics, the numbers we all learned about when we were kids. So we start walking in the positive direction, and right away we find them. 1, 2, 3, 4. You know, the counting numbers. They go on forever. So we just scoop this whole infinite bunch right into our bag. In the math world, this collection has a name, the natural numbers. We just call them n.
Hang on a second. Wait, we missed one. Right back where we started. Let's turn around. Yep, there it is, 0. We gotta grab 0 and toss it in the bag. And just like that, our collection is a little bigger. It's not just the natural numbers anymore. Now we have the whole numbers. We call them W. It seems like a small change, but trust me, it's a huge deal.
Okay, bag's getting heavier. Now let's spin around and face the other way from 0. Whoa, look at that. A whole other infinite road of numbers stretching out in front of us. -1, -2, -3, all the way to infinity. Let's scoop all of those up. Now our bag is holding what we call the integers. Fun fact, they get the letter Z from the German word zahlen, which just means to count.
All right, our bag is starting to feel pretty full, right? We've got all the positive and negative whole numbers, but take a closer look at our road at the number line. See all that space between 1 and 2, or between 0 and -1? There are still these huge gaps everywhere.
So what's in those gaps? Well, that's where all the fractions and decimals live. You know, numbers like 1/2, or -3/4, or even 5.2. We call these the rational numbers. Basically, if you can write a number as a fraction, a ratio, it's a rational number. That's why they get the letter Q, which stands for quotient.
And here's the really cool thing about these rational numbers. When you write them as decimals, they're super predictable. They always do one of two things. They either just stop, like 1/2 is just 0.5, the end. Or they go on forever, but in a repeating pattern. Like 1/3 is 0.33333, just threes forever. That predictability, that's their signature move.
Okay, so now our bag is practically bursting. We've got the integers, and we've stuffed all the fractions and decimals in between them. It really feels like we've filled in every possible gap on this line. We're done, right? The number line is complete, isn't it?
Nope, not even close. Because thousands of years ago, the ancient Greeks stumbled onto something that would completely blow their minds and shake up everything they thought they knew about math.
You see, there was this group, kind of like a secret club for math nerds, called the Pythagoreans, and they discovered numbers that just broke the rules. Numbers you couldn't write as a simple fraction. The square root of 2 was a big one. And for them, this wasn't just a fun puzzle, it was a full-blown crisis. Their entire worldview was based on the idea that the whole universe could be explained with nice, neat ratios. And if you want to know how serious they were about this, legend has it that the guy who let the secret out, a fellow named Hippicus, was thrown off a boat and drowned. Just for revealing that these numbers existed, they were not ready for this. So what are these mysterious, forbidden numbers? We call them the irrational numbers. And here's the kicker. Their decimals go on forever, kind of like some rationals do. And this is the whole point, they never fall into a repeating pattern, ever. They're just beautifully chaotic, unpredictable strings of digits. And you actually know some of these. The square root of 2 is a classic. The most famous one, of course, is pi. Yep, 3.14159, that number you use for circles, totally irrational. And you can even invent your own, like this one here, 0.101101110111 dots. See how the pattern keeps changing just enough so it never truly repeats? That's an irrational number. So now we have this last kind of weird set of numbers. And with these in hand, we can finally complete our collection and see the whole picture. So let's toss all these irrational numbers into our bag.
What we have now, all together, is the complete set of real numbers. We give them the letter R. And this is the big takeaway. Every single number on that line is either rational or irrational. It has to be one or the other. There's no third option.
And just like that, our number line is finished. It's totally complete. Every tiny microscopic point on that infinite road has a name. It's a real number. There are no gaps left. Our bag is full. The collection part of our journey is done.
Okay, so we've got our map of the entire real number landscape. That's awesome. Now let's switch gears a bit. Let's talk about a super powerful tool we can use to work with all these numbers we just collected, especially when they get really, really big or really, really small. Let's talk about exponents.
So what are exponents? Honestly, they're just a shortcut. It's a way to write repeated multiplication without getting a hand cramp. That little number up top, the exponent, just tells you how many times to multiply the big number, the base, by itself. So 2 to the 4th power, it's just 2 times 2 times 2 times 2. Simple as that.
And the best part? Exponents have these really simple, clean rules that make them super easy to work with. Like, if you're multiplying two powers that have the same base, you just add the exponents together. Super easy. And there are a couple of cool little tricks too. A negative exponent? That just means you flip the number and make it a fraction. And my favorite, any number raised to the power of 0 is always 1. It's kind of weird, but it's a rule. These laws make life so much easier.
Okay, so why should you care about any of this? Well, imagine you're a scientist and you have to deal with a number like this one, 3,200,000. I mean, can you imagine writing that out over and over again in your calculations? It's just clunky. There's got to be a better way, right? And of course there is. This is where exponents become a superhero. We can use them to rewrite that huge number in a much cleaner way. 3.2 times 10 to the 6th power. This is called scientific notation, and it is an absolute game changer. It's how scientists and engineers deal with massive numbers, like the distance to a star, or tiny numbers, like the size of an atom, without losing their minds.
So, let's recap. We've taken a whole journey down the number line, from the simplest counting numbers all the way to those weird irrational ones. We've bagged them all, and we've even picked up a powerful tool, exponents, to help us manage them. It just goes to show you, even something as simple as a line can hold an entire universe of ideas. So it makes you wonder, what other mathematical worlds are out there, just waiting for us to explore? Maybe if we step off the line,